Hey guys, and welcome to your first lecture of the intermediate algebra course. Today we are doing 1.2. The learning objectives are identifying and evaluating algebraic expressions, writing phrases as algebraic expressions, writing the opposite of a number, finding the absolute value of a real number. So it's important to understand the definition of those absolute value bars around a number or around a variable. We will also just quickly cover natural numbers, whole numbers, integers, rational numbers, and irrational numbers. These are all real numbers, and it's just a way of grouping real numbers. So welcome, and I hope that you enjoy this and feel ready for the semester. Sorry, I was trying to figure out why that face camera kept going out of focus, but I guess it doesn't matter because this camera will stay in focus, and that is the important thing. All right, so I think I already read these learning objectives to you. We are going to, we're just going to do some writing, some identifying, and a little bit of evaluating. Algebraic expressions. In algebra, when we don't know the value of a number, we use a letter to represent that number. And then a constant is a fixed number or a letter that represents a fixed number, and a constant does not change. An algebraic expression is formed by numbers and variables connected by the operations of addition, subtraction, multiplication, division. Those are the common ones, right? Or raising to powers, which looks like this, or taking roots, which looks like this. So an algebraic expression is made up of variables, constants, and operations is what we call all of these. These are operations. Good. So here, x represents some number that we do not know, right? So the way I would say this as a sentence is some number multiplied by 3 with 5 added to it, or a number multiplied by 3 plus 5. Either of those kind of mean the same thing. Here we have a number raised to a power, so it would be raised to the second power, multiplied by 5 minus 6 times that same number plus 40. Here, the fraction bar is also a division symbol. So anytime you see a fraction, you're just seeing a division problem. So here we have a number raised to the 4th power minus that same number raised to the 2nd power plus 15, all that quantity over 4 times that number. That's how we would say that one. All right, an algebraic expression is actually different than let me show you. So we have 3x plus 5, right? Tell me the difference between this and 3x plus 5 equals 14. This is an algebraic expression, and this is an algebraic equation. An equation will always have an equal sign. An expression does not have an equal sign. If our algebra lacks an equal sign, we cannot solve it. I cannot find out what x is if I can't set 3x plus 5 equal to some number, right? So algebraic expressions cannot be solved. We can only simplify it by raising it, or sorry, simplify it by combining like terms, or we can evaluate it by substituting in a value in place of the variable, right? If I said x is 4, then I can evaluate it. So we call it solving if we find x, we call it evaluating if we take x and find a different number. I guess my room must be really dark and confusing all of my cameras. All right, any questions about this, please email me, just note down the question. Alternately, if this is all review for you, I encourage you not to write down any notes if you already know it by heart. If you're listening to this and nothing's really new, nothing is confusing, you don't feel obligated to write everything down. The reason you want to take notes is so that you can look back on this later and remember, oh, that's what that means. But if you are fully clear on what everything means in this example, you know, you don't necessarily need to write everything I write down. All right. So for example 1, we are going to evaluate this expression. The expression is L times W. Actually, we can turn it into an equation because it's area equals length times width, right? So we just took it from an expression to an equation. All right, so our evaluation is the area of a rectangle with length L and width W is L times W. If it's right next to each other, it means multiply. LW means multiply. L with a little dot between them. W means multiply, and then parentheses L, parentheses W side by side means multiply. We don't necessarily use this one in algebra to mean multiply because we're already using X as a variable. So the most common variable is actually X. We also like to use Y, we like to use Z, we use A, B, or C. You can use whatever letter you want. If it's a word problem and you're actually using it to replace something, and you can use like the first letter of the idea, right? Like if we're talking about money, we could use M. All right. So LW means length times width. Find the area of a rectangle with length 5 meters and width 3.2 meters. All right, so we know area equals length times width. Length is 5 meters. And I need to add that M, right? Because we know that if this is 5 and this is 3.2, our answer is going to be a number meters. It was 5 meters, 3.2 meters. We know our answer is going to be meters squared, right? So 5 meters times, I like parentheses, 3.2 meters. I especially like parentheses if it's a letter right next to another letter or a letter right next to a number because, well, I'll just show you later. So we have 5 times 3.2. And you get 16. So A is 16. A meter times a meter is a meter squared. Anything times itself is raised to the second power. And we are done. This, yeah, M is a known value, so that's not really a variable. That just is short for meters. All right. So we just evaluated an area equation. Now we're going to evaluate B minus 5A when A is 4 and B is 35. So we're going to now say 35 minus 5 times 4. So the reason I like parentheses is it's not 35 minus 54, right? It's 35 minus 5 times 4. So that becomes 35 minus 5 times 4 is 20. 35 minus 20 is 15, right? Yeah. So anything pushed up against each other with nothing else means multiply with no sign in between them. Ooh, already on the number line. All right, this is a number line. A number line is a line on which each point is associated with a number. Any number you can imagine is on this number line, right? The numbers going this direction are always negative, and as you go this direction, they become positive, or they go higher, right? And here they go lower. So we have negative numbers to the left, positive numbers to the right, and between them is 0, which is not negative or positive. It's just 0. 0 is not negative or positive. It's just 0. Okay. So these, the whole numbers, the numbers that are not decimals, not fractions, we say they are identified on the number line, right? And then you have numbers like 4.8, or sorry, negative 4.8. It's not really identified. We just know, 0.8. It's between -4 and -5. It's closer to -5. I'm just going to say it's right here, -4.8. 1.5, I know it's between 1 and 2, and it's exactly halfway because 5 is halfway between 1 and 10. So that's right there. Good. All right. So this now becomes the real number system. Okay. And we're going to come back to it. But what this note, slide 6, is talking about is objects of a set. Okay. The objects of a set are called its members or its elements. Okay. So this means element. And this symbol means set. Okay. So we are just talking about all the numbers of a set. A set is a group of numbers, all the numbers in a group. That's the word I was looking for. All right, so we have 2 forms to write a set or a group in. We have roster form. Roster form means we're just going to put every single element of the set in between the brackets, right? So I'll start with 12, 13, 14, 15, 16. All right. That's my roster form. I have listed every element in the set between all natural numbers between 12 and 16, right? Set builder notation describes the elements of the set. Yeah. So this little symbol right here means such that. Such that, and then you go on to describe the set. Okay, so here we have the natural numbers between, we have the natural numbers between 11 and 17. The natural numbers between 11 and 17. If I wanted to write that same expression in set builder notation, I would still use those brackets, but I would say x such that x is a natural number between 3 and 8. No, sorry. I was reading my notes and my notes had a different example. Between 11, I tried to make up an example, and 17, right? It's between, it doesn't include. So we don't say between 12 and 16, we say between 11 and 17. So these are the same group. It's just 2 different ways to write that group or to write that set. And then we say the element, it's like, we have to give this set a name. So set A, we'll say set A, and here's set A. Good. So now we're saying, 14 is an element of set A. 20 is not an element of set A. Good. The brackets let us know we're working with a set. The element symbol tells us we're talking about one part of the set, or if it has a strike through it, one part that is not within the set. Good. And remember, I'm going to come back to these and just a moment. All right. All right, for the examples, write each set in roster form. So they are currently in set builder notation is the description, and we're going to put it into roster form. X such that X is a whole number between 1 and 8. So we still use those brackets, a whole number between 1 and 8. So I'm not going to include 1. I'm going to start with 2 and only use whole numbers. So that does mean I need to go back to this. Whole numbers are 0, 1, 2, 3, 4, continuing in the same fashion forever. Whole numbers. Yeah. When you see these 3 ellipses, it means continuing in this, how would you say it? Continuing in this pattern forever? Yeah, in this way forever. You're gonna get a lot of infinity in this class, right? So our pattern is 1, and then we add 1, add 1, add 1, add 1, 6. We're gonna add 1, get 7, 8, 9, and we continue in this way forever. So natural numbers are anything you can use to count. Whole numbers are natural numbers and 0. Integers are whole numbers and all the negative numbers. But notice there are no fractions, no decimals, okay? So X is a whole number between 1 and 8. We need all of them. 2, 3, 4, 5, 6, and 7, and then you close the set. Good. X is a natural number. So the natural numbers do not, the natural numbers do not include 0. X is a natural number greater than 100. And as we just looked at over there, if you make your pattern clear, so my pattern right now is clear, I'm just adding 1. And then you do 3 ellipses. You're saying continuing in this way forever. These are all natural numbers greater than 100 in this set because I started listing them in a direct pattern and then I added 3 points, added an ellipses. Good. All right. Determine whether each statement is true or false. 0 is a member of the set, is an element, sorry, we should use the word element. 0 is an element of the set X such that X is a natural number. Let's look at natural numbers again. Sorry, I'm writing. All right. Natural numbers, 1 to infinity. 0 is a natural number. This is false. Yeah. All right. 9 is an element of the set 4, 6, 8, 10. False. Right? All right. So we have now real numbers, rational numbers, irrational numbers. And the reason I waited on these is because these are all the same topic. All right. So I want to make, I'm going to take a little note card and I'm going to make just a little diagram of what these are. Okay. So real numbers, the set of all rational and irrational numbers. If you had a number line, anything you put on that number line is a real number. Any number you can imagine. All numbers are real numbers, okay? And then we're going to split those real numbers into rational numbers and irrational numbers, okay? Rational numbers are numbers that can be expressed as a quotient of integers. When written as a decimal, the decimal will either end or repeat. A quotient means division, right? So rational numbers are the division of 2 different numbers. And so that's this side of the real numbers. On the other side of the real numbers, the other group is called irrational. It's not just one number divided by another. It's not written in, it's not a repeating decimal, and it's a decimal that never ends, okay? So on my calculator, I have, oh, pi is a good irrational number. All right, so here is the button pi on my calculator. It's an irrational number. The decimal never repeats. What I want to show you is how many numbers after the decimal there are on my calculator. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I'm going to do another irrational number. I'm going to do the square root of 2. 1, 2, 3, 4, 5, 6, 7, 8, 9. That also has 9 digits behind the decimal. That's because the float of my calculator is set such that it always stops and rounds off at 9. So an irrational number, when you put it in your calculator will give you every number it's allowed to give you, and then it will round it. If you don't see a pattern in the number your calculator gives you, it's an irrational number. If you can see a pattern, like 3 divided by, nope, 2/3. I see a pattern. It rounded to 7 at the end because 6, 6 would round to 7, right? So that's a pattern. Or 1/2 is a decimal that ends. Even the number 5, that ends with a 0 decimal right after the decimal. So these are rational numbers, these 3, but the square root, the square root of 10 is rational because it ends. 1, 2, 3, 4, 5, 6, 7, 8. And the square root of 2 is irrational because it doesn't end because you got 9. There you go. Irrational, rational. It ends, it does not end. Okay. So those are the 2 groups. We have all real numbers. We have rational numbers here, irrational numbers here. Within rational numbers now, we have natural numbers, whole numbers, and integers. Okay. The smallest group we have is actually the natural numbers group. Okay. So natural numbers are the smallest group. These are natural numbers. 1, 2, 3. Okay. And then with all the natural numbers plus 0, that means whole numbers. Those are called whole numbers. So now there's a group here called whole numbers. And now it's 0, 1, 2, 3, continuing in this fashion forever. Good. And then we have integers, which is all the whole numbers plus the negatives. These are integers. And so that will be -3, -2, -1, 0, 1, 2, continuing in this fashion forever. Those are the integers. And then all integers are rational numbers. So rational numbers are expressed as a quotient of integers. So like we said, 2/3, 1/2, 5.3, any decimal that ends, and any fraction you can invent is a rational number. And then however, over here, so I wrote it small. I wrote it so small yet way too big. Over here, we have the irrational numbers, everything else. And that's, remember, your pi, your square root of 2, anything that cannot be a fraction and that goes on forever if it is a decimal, okay? And both of these groups, so this doesn't have any subgroups, but both of these groups are just called real numbers. Good. And these are all real numbers. Anything you can dream of is a real number. Good. So I just wanted you to see. So we have real, rational, integer, whole, natural. Okay. Is this true or false? 0 is a real number. The real numbers are everything. Everything is a real number. Is 0 a real number? Yes, it is. So we're going to say that is true. Every integer is a rational number. Every integer is a rational number. Yes. The square root of 3 is a rational number. I don't really know. Put it in my calculator. Because it turns out the square root of 10 is a rational number. The square root of 3 is not. Or sorry, square root of 2 is not. So look at square root of 3. It is not. It goes as far as my calculator will allow itself to go. So we have a true, and a false. All right, we said we would talk about absolute value today. The absolute value of a real number A, denoted by A between the absolute value bars, is the distance between A and 0. So -4 within the absolute value bars, when we take it out of the absolute value bars, we get a +4, right? +5 within the absolute value bars, when we take it out, it's a +5. So you could just say, it's just like an automatic positive, right? Just make sure it's positive. If it comes out of here, it becomes positive. Why is that true? Because we're talking about distance. The absolute value is always the distance between that term and 0 on the number line, okay? So when we're looking at distance, distance is just never negative, right? If I'm measuring something with a ruler, my ruler doesn't have any negative numbers on it, right? If you want to measure the table in front of you right now, and you start on the left side and you measure to the right, and you get 10, I don't know, inches, and then you go from the right side and you measure to the left, do you get -10 inches? No, either way you measure, you just get 10 inches, right? If I drive to school and I put 10 miles on my odometer of my car and I drive home, I'm going to put another 10 miles on, not -10, right? So all we're saying is -4 is 4 away from 0. 5 is 5 away from 0. The absolute value of 7 is 7. The absolute value of -6 is 6. The absolute value of -4/5 is 4/5. The absolute value of 0 is 0, because 0 is 0 units away from 0. All right. Opposites or additive inverses. These are two terms you can exchange. We obviously use opposite more than we use additive inverse, but additive inverse is just more technical, so more technically accurate, I guess you could say. So there are two numbers that are the same distance from 0, but lie on opposite sides of 0. We call it an additive inverse because if you took the inverse or the opposite of the number and added it to that number, you would get 0 again, okay? The opposite of a number A is the number -A. For every real number A, negative A will equal A. Yeah, two negatives become positive. Write the opposite of each number. The opposite of -35 is 35. The opposite of 12 is -12. The opposite of -3/11 is 3/11. Just a note here, -3/11 is -3/11 is 3/11. It doesn't matter where the negative sign is. It could be in front, on top, or on the bottom. Because negative, we don't need a cosine here. -3/11 looks like that. -3 divided by 11 looks like that. 3 divided by -11 looks like that. So it really doesn't matter. All right. The inverse of 1.9 is -1.9. All right, here's where we go back to translating. Here are different terms for our 4 symbols of addition, subtraction, multiplication, and division. We have sum, we have plus, we have added to, we have more than, we have increased by, and we have total. Subtraction, we have difference, minus, subtract, less than, decreased by, and less. All right, multiplication, we have product, times, multiply, multiplied by, of, double, which only means 2, right? Or triple, which means times 3. Division, we have quotient, divide, shared equally among, divided by, and divided into, okay? So write each one as an expression. X represents an unknown number. 5 decreased by a number. And they said, let X represent the unknown number. And it's an expression, so it will have no equal sign. Don't worry about the equal sign. The quotient of a number and 12, or X over 12. Good. All right. Example 9. Translate them into algebraic expressions again. The sum of so here we have the sum of 4 and twice y. The sum of 4 and twice y. Here we have x less than the product of y and z. So if I said 5 less than, am I putting the subtraction sign here or here? 5 less than here. X less than, sorry, I was trying to make that. 5x less than the product of, we have another one. The product of y and z. Y times z minus x. Good. And you could put parentheses around the product of. Three times the difference of a number and 10. The difference of a number. So here's my number. The difference of a number and 10 means x minus 10 or 10 minus x. The difference between a number and 10. 3 times the difference of, so I have to put parentheses around this because I want to distribute the 3 to the x and the negative 10, or I want to do this first and then multiply 3 times all of that, okay? Here we have 1/4 subtracted from, they really are testing us with the subtracted from, subtracted from 3 times a number. And remember, they told us our number was x. 3 times a number. I don't really need parentheses until I replace that x with a number. Good. That's the end. Let me switch my video. Oh, I had to charge my, okay. Guys, thank you so much for watching the full video. I hope you feel very set up for the rest of our semester. See you next time.